Okay, now let's move on and start talking about really the content or the subject of the rest of the course, and that is the idea of some programming language that we use to create the instructions that a computer is going to follow. So, software is written in some programming language. And a programming language is just an artificial language created by humans that the computer happens to understand too. So these programs that we write ultimately represent the specific instructions on how the computer should solve a given problem. And we have to be very exact with that because the computer really doesn't have any intuition or independent thought capabilities. So we have to be completely explicit with what it's supposed to do next, step by step, in order to solve any particular problem. Now, as computers have evolved or gotten more sophisticated over the years, so have the programming languages used to program them. So let's start at the beginning. Our first and lowest level, or closest to the hardware programming language, was something called machine language. And in machine language, basically we just take the instructions that the computer knows how to do and write our programs using those instructions. Every CPU, every computer, has a series of binary patterns it understands as instructions, and those are called its instruction set. And so all you have to do is somehow write down all the instructions that you want the computer to follow in order. And then when the computer reads those instructions with its fetch, decode, execute, and store cycle, it can solve the problem by following your instructions. Simple, right? Well, not really. If we take a look at machine language, we find that it's really unfriendly. So here are the first few bytes of a program that displays 2 words on the screen out of about 16,000. Now obviously those bytes to us are super unreadable. It's very difficult for us to understand what's going on with those. So machine language is not human friendly. That's what the computer understands, but not us. So we need to have a better solution. And our first better solution was to use some sort of mnemonic to represent each of those instructions instead of the binary. So you sort of slap a 3 or 4 character name onto each of those instructions, and then that becomes more useful for humans. Of course, the computer doesn't understand the mnemonics, so this assembly language has to be run through another special program called an assembler. And that takes those mnemonics and translates them into machine language. So that gets a little circular, doesn't it? We have to write a program called an assembler that takes in other programs in assembly language and translates them into machine language. So the first assembler had to be written in machine language. Here's a sample. This is a sample assembly language program that computes a difference. And so it creates 2 variables, j and k, and then a third called the difference. Starts off a program, puts the number 20 into j, the number 12 into k, then takes whatever's in the variable j, the location, moves it into another location called diff, subtracts k from that. So at the end, this storage location named diff will have the difference between 20 and 12, or it should contain 8. Okay, so that's a little bit easier to understand than the binary. At least these look like something that sort of mean things to people. MOV probably means move, SUB might mean subtract, exit, end, and so on. Okay, but it's still not super friendly. And the other problem is that it's not portable. So this assembly language corresponds directly to machine language, which is tied directly to one type of a processor. So if I was writing a program that was going to run on my mobile phone and on my laptop, I would have to use different assembly languages because they have different processors. So that's not acceptable. So we move up another level where we use a more natural words to represent actions, and that's called a high-level language. And then we have another special program called a compiler that translates that program into machine language. Or maybe it goes first to assembly language, which is then assembled. Okay, but the nice thing about a high-level language is it's not tied to the underlying machine language directly. So we can write a program and then compile it to run on different platforms. So the program becomes portable. We can move it from one place to another, one computer to another. So here's a sample. This is in the programming language called Fortran, and it converts a temperature in degrees Fahrenheit into degrees Celsius. So this says I have two real numbers, F and C. I read one, my temperature in degrees Fahrenheit, calculate the degrees Celsius, and then print out the result. So this is much more readable than even the assembly language was, which is nice. So high-level languages are where we're at. Okay. Our programming language that we're using is called processing. And processing is a free language, and it has free development tools, which are all downloadable from the website at www.processing.org. It'll run on Windows machines, it'll run on Macintoshes, it'll even run on Linux boxes. So it's multi-platform free, which is cool. Another thing that's nice about processing is it's based on Java, the Java programming language, which is very popular, used not only for desktop development, but also Android mobile devices. Those programs are written in Java, so it's a very handy language to know how to do. The cool thing about processing, other than it's free, is that it lets us do graphics, sounds, music, interaction very easily. And that makes programming more fun, at least more fun than it would be with a traditional language. So let's illustrate that real quickly. Here's two examples. The first one is our standard canonical first program. Most programming courses, they'll have you write this program as your first ever program. It just prints out two words, hello world, on the screen. And let's see how we would do that in Java. So here's our interface for writing programs, and this is in a development environment called NetBeans. And you'll notice that a program really is just a series of words typed into a fancy text editor. And so part of this program is already written. I'm just going to finish it up. I'm going to give it the instructions on how to print out something to the screen and have it print out hello world. And there's my program, and then I can make it run by clicking on a special button on this integrated development environment. And when I click the run button, my program is compiled, and then down here is the output. Isn't that exciting? And no, it isn't, and that's the point. It's kind of boring to see text on a screen like this. It's like we're using a teletype, and teletypes haven't been used in a long time. So why should we program like that? Instead, let's take a look at a simple graphics program in the processing language. So here's a processing program. First of all, you notice that its interface is really quite a lot simpler than the interface was for our Java programming environment, and that's nice. Not as much to learn about. We are still typing in words, so I'm just going to have this create a window that's 500 by 500 pixels in size, and then to show some graphics, I'll have it sort of animate a line that goes from the center of the screen to wherever my mouse pointer is. And let's make that line red. Okay, so here's a simple sketch, simple processing program. And now when it runs, we'll see that it's actually graphical, and my little line is following my mouse pointer. And so those types of programs are really easy to do in processing, which makes it a lot more fun to deal with. Okay? So this is the language that we're going to be using, and we'll be doing some really neat stuff with it pretty quickly. Before we finish, it's really important to note that you don't just sit down and start writing code. This course is really about problem solving, learning how to solve problems, and then we just happen to implement those solutions in a programming language. So we're going to follow a framework called the RADIS problem solving framework. It's a series of steps we can use to solve pretty much any problem, not just computer problems. And it goes like this. It's an acronym. The R stands for recognize. And in that step, we have to figure out what problem we're trying to solve. If you don't understand the problem, it's not very likely that you're going to get the right solution. Okay? And that works in math, it works in physics, it works in computer programming. The first thing you have to do is start out with understanding the problem. After that, we analyze things. Look at what are the different options for solving it. What tools will we need? Will we need a database? Will we need access to a network? What would it cost? If we're in the real world, would we have to hire new people to do this? So on. After we've got all those things figured out, then we move on to a design phase. And that's where we sort of make a recipe that the computer follows in order to solve its problem. What are the steps, in what order, that the computer has to execute in order to solve this problem? Okay? Only after we do all of that can we implement it. That's when we write the code. So if we do a good job with recognizing, analyzing, and designing, then the implement part should be pretty simple. The S stands for support, and that's where we would fix bugs, add features, and so on. Because software never dies, particularly good software lasts forever, and so it needs to be maintained. All right? Now, this RADIS framework isn't always linear. In fact, it's rarely linear. You'll do some circling around here in the analyze and design phases. Maybe forget something, or change your mind, or get into a little implementation and decide that it's not really the way you wanted it, so you have to backtrack. But conceptually, these are the steps that we're going to use in order to solve problems. All of the examples that we do throughout the course will be based on this RADIS problem-solving framework. All right? So now we can move on and start writing some programs.